All right, let's take a look at example 3. It says use the function below to find any vertical asymptotes that exist and then justify your answer using limits, okay? All right, so just like if we had this in limit form, we would try to factor the bottom and the top. So I'm just going to factor this quickly. So this would end up being 2x minus 1 and x plus 5 at the top, and then at the bottom, x plus 5 and x minus 2. Okay, so a couple things here. Make sure that you're aware that that's creating a hole at -5. Okay, so that would not be any kind of infinity. All right, so we're left with 2x minus 1 over x minus 2. So the factor x minus 2 doesn't cancel. So it's whatever makes this 0, which of course is 2. All right, so there's some kind of vertical asymptote happening at 2. All right, so what we're going to have to do is note that that's how we're going to answer the question, and then we're going to justify it using limit notation. So we're just going to say at x equals 2 there is a vertical asymptote. Okay, so we've just identified where it's at, and now we're going to justify that using limit notation. So what we're going to have to do is look from the left, look from the right, and we'll say h, and I'm just going to organize it over here. So this is like x, this is like h of x. We'll plug in like 1.9 and 2.1, something like that. If you plug in 1.9, you'll get positive over negative, which of course is negative, and then if you plug in 2.1, you'll get positive over positive, which of course is going to be positive. So as you approach from the left, this equals negative infinity. If you approach from the right, it equals positive infinity. Okay, just kind of using the new definition with limits to justify the vertical asymptote. Okay, so nothing crazy there. You've seen this a bunch of times. So what you haven't seen before is the second part, which is limits at infinity. Okay, this is when the limit is approaching infinity. All right, so you have done this on a graph, but we haven't done this yet analytically. All right, when I just give you the algebra. So there's going to be a couple things we need to recall from functions and from finding asymptotes. Okay. All right, let's take a look. So at A, we need to know what kind of function these examples are going to be, all right, at least in the first couple. So if I was to simplify this, the first thing I would do is FOIL, right? If I wanted to get this more simple, and then I'd end up with x to the 4th. Okay, that's the highest power of this polynomial, okay? It's also called the degree. So this is a degree 4 polynomial. Right, it's also known as a quartic function, right? You're probably more familiar with quadratics. We use that every single day, but a degree 4 is called a quartic function, okay, or a quartic polynomial, all right? So what we need to know about this is that a quartic function is going to basically look something like this. It's going to look like a parabola. Okay, and we know it's going to be shooting up because the leading coefficient is +1. If it was negative, it'd be shooting down. So the two things we need to know is that it's quartic, so it's going to look like a parabola, and it's shooting up. So this is going to be going to positive infinity in both directions. All right, it's going to be rising on the left and the right. All right, so we're only looking in this particular case at infinity, so we know it's going to be shooting to positive infinity there. All right, so we have to kind of analyze this graphically. All right, so the limit would equal positive infinity. All right, it's just any even-powered polynomial is going to be some type of parabola, and then we want to take a look at the leading coefficient to see if it's shooting up or down. All right, so in part B, it's a similar idea. The degree here is 3. It's the highest power, and we know that degree 3 polynomials look something like this, okay? So since it's going in this direction, it's just a transformation. There's no flips, so there's nothing negative here happening. So it's not flipping over the y or the x-axis. So that's what the graph kind of looks like, and then we're looking toward negative infinity. So shooting down this way, and that's also going to negative infinity, right? It's going to fall to the left when you have an odd-powered function that hasn't been transformed or flipped or rotated or anything. Okay. All right, and then the other piece here. So notice that these are rational. Okay, so this is a little bit of pre-calculus knowledge. Here we have a rational. In the top, the degree is 2, and in the bottom, the degree is 2. Okay, so if you're looking for a horizontal asymptote, then we're going to take the ratio of the coefficients. Okay, all right, so here we're basically just going to focus on this piece. All right, the -4 at the top and the +1 at the bottom don't really matter because we're looking at infinity, right? We're looking at the end behavior. So the -4 and the 1, they're relevant overall for some things, but as far as looking at the end, whether or not it's shooting up somewhere or if there's some horizontal asymptote, that doesn't really matter. So we're just going to focus on the 3x squared and the x squared. Okay, so there's a couple situations where you could be in. So here the degree is the same in the top and the bottom. So if I look at this here, so 3x squared over x squared, what I'm going to concern myself with is the ratio of the coefficients when the degrees are the same, right? So we're going to end up with 3 over 1. So what that means is, so I'm going to write a couple things. So when the degree of a numerator is equal to the degree of denominator, there is a horizontal asymptote, I'll just shorten it with HA, at the ratio of coefficients. Okay, that's only when they're the same. All right, so in this particular case, there's a horizontal asymptote at y equals 3, okay, or 3 over 1. All right, so as you're looking at, as x goes to infinity, y is going to be approaching 3, okay, because we have, oh, look at that, Southeastern email. It's going to be approaching 3 because there's going to be a horizontal asymptote there. All right, and we were able to figure that out because the degrees were the same. So this limit is going to equal to 3. All right, so on your paper, when you start doing this on Monday, take a look at, when you're looking as x goes to some type of infinity, whether it's positive or negative, and it's rational, take a look at the degrees, okay? In this case, they were the same. In part D, they're not, right? So we have a linear at the top, and then we have a quadratic at the bottom, okay? I know just by looking at this that this is going to be equal to 0, okay, because I'm doing that analysis with the first terms, okay? Now notice that the 5x, that power is 1, and then here at the bottom, the power is 2, okay? So I'm going to write a couple things down here. When the denominator degree is greater than the numerator degree, then y equals 0 is a horizontal asymptote. Okay? So essentially, when you're looking at this and you're trying to analyze the degrees, the degree in the top, if that one's higher, then the function is shooting to positive infinity. All right? It's a more powerful power at the top. If the degree in the denominator is higher, then it's shooting it down to 0 faster. All right, so it's almost like the function is battling. So when the function's degrees are the same, we take the ratio, and then if they're not, we're going to take a look at which one is more powerful. All right, if the more powerful one is in the denominator, like it is here, then it's y equals 0. If the more powerful one is in the numerator, then it's going to be infinity.